Our next speaker is Amit Apte, my former colleague. Now he is holding the position of chair in IISER Pune, Department of Data Science. Amit obtained his PhD from University of Texas at Austin, and then he did his postdoc at University of North Carolina at Chapel Hills. His main areas of research are data assimilation and dynamical systems in earth sciences. So he was in TIFR CAM and then also in ICTS Bangalore, and recently he moved to IISER Pune. Today he is going to speak about machine learning methods in data assimilation. Over to you, Amit.
Okay. Yeah. Thanks a lot, Datti, for the introduction. Can you hear me and can you see my screen?
Yeah.
Okay. Thanks.
Yeah,
okay.
It's fine. It's fine.
Okay. Yeah. So I guess there are these two pieces: machine learning methods and data assimilation. And in some sense, when I joined TIFR CAM, Vasu was the one who was very interested in these data assimilation methods. In fact, we talked a lot about it. We finally never managed to write a paper together on this at all. But the discussions with him were extremely motivating and always very resourceful. Essentially, anytime I would be stuck on something, I can go to him and he would immediately find references and citations and papers to look at and find a way of if I was stuck somewhere. So that's one thing. The other was the machine learning. And I wasn't in touch with Vasu academically a lot for the last maybe 3-4 years or so. But one of the things that he sent me maybe 3 years ago was a summer project that he did with his students, and I guess he continued afterwards, was trying to use machine learning methods in dynamical systems. And so he was very much modern in his lookout in terms of the kind of problems he would understand, he would try to address. And of course, his deep knowledge of mathematics combined with his deep knowledge of many other fields would lead to very fruitful and useful results. So in some sense, both of these words in the title have influence from what I discussed with Vasu and what he actually also worked on with his students and his colleagues. So, okay, with that, let me just start by saying that this is basically joint work with my students at ICTS, Pinak Mandal and Shashank Roy. And okay, so let's get going. Just a definition, many of you may have seen this before if you have heard a talk from me. Data assimilation, essentially it's a nonlinear filtering theory problem, if you could mathematically state it. But the main challenges is what I'm trying to capture in this definition. Of course, we have partial and noisy observational data that we want to do something with. And I guess noisy is probably redundant. There is no non-noisy data, and partial is also usually redundant anyway. But this is a system which is of the type that comes up commonly in earth sciences. It's a complex system, non-linear, of course, and chaotic, usually deterministic dynamical system. And so combining these partial noisy observations along with the dynamics of the system, and what do I mean by dynamics? The imperfect model of the dynamics of the system that we have. So combining these three, the data assimilation problem is to try to get a state estimate and the associated uncertainty for the system state. So that's in a way the definition. So I will start off by laying out the mathematical framework for this problem, and in particular, what are the main mathematical challenges in this problem. So as I said, the statement itself is nonlinear filtering. So maybe 50 years ago, it was well stated mathematical problem, but the challenges continue to be severe even to this day. So that's one thing. I will talk about why stability is important property. It's not I think given the audience here, I don't really have to convince people that stability is a useful and important issue for almost all numerical systems in general, but I'll talk in particular about what is numerical stability of filters and how to assess it numerically. And towards the end, talk about some recent work on trying to use neural networks for addressing the data assimilation problem. And this is still work in progress. I'll show a part of what the results we have until now and discuss a bit about the future directions. Okay. So the main mathematical problem is basically as follows. We have a dynamical model, a dynamical system, which is time evolving, and this could be either a deterministic or a probabilistic dynamical system. So M here could be either deterministic map or a probabilistic model given by a Markov transition kernel. And given this dynamical model, that is, so say M is in either M or the transition kernel PM is assumed to be given to us. And this is the either in the context of earth sciences, this will be the solution for a PDE, or in the context of biology, these could be ODEs for certain dynamical systems and so on. And what we have along with this model that we have that is given are the observations of the state over a certain time period. And given, of course, the observations are local in time, in the sense that the observation at time t depends only on the state at time t, and there are no memory effects in the observation process. And but of course the observations are noisy, and I'm just talking about the additive noise case. Multiplicative noise gets significantly more complicated. Usually the relation between the observations and dynamical models sufficiently overshadows in some sense the noise in the observation that is put in. So this is at this stage, this is a sufficient representation. And so given these observations, the problem is to estimate the state xt at some time t given these observations. So just a few. Okay, so I guess I'll not talk about smoothing and prediction at all, but let me just jump to what exactly is filtering. And so the main object in data of interest is estimating the state at time t given observations up to time t. So this is a shorthand for all the observations up to time t. And the Bayesian answer to this is best to look at the posterior distribution of the state given the observations. And this will be the main object of interest. And this is essentially filtering theory in discrete time. As I said, I will not really talk about smoothing or prediction problems or a deterministic formulation of this same problem, which will be, in a sense, an inverse problem to find a mapping from the observations to the state. But those are not discussed here. Is there a question? I'm fine with having questions in the middle, so please go ahead and ask questions. That's okay with me. But I couldn't hear it. Okay, fine. So so the this conditional density essentially itself can be thought of as a dynamical system, in the sense that given the filter or the conditional density at time t minus 1, we would like to get the conditional density at time t. Sorry, this should have been x, not 1 through t, but just xt. And this is done usually in two steps. One is a prediction, and the other is update or base update. And in the first part, we only use the Markov model. This is simply going forward in time using the Markov model. Given the state at time t minus 1, we know how to get the state at time t. That's basically the model that we have. So it's basically model integration. And so that step in principle essentially is what we already have with us. For example, just think of this as a solution of a PDE. Right? Of course, we don't think of solution of PDE written like this. It's that you have a probability density at time t minus 1, which is then probability density at time t. And if you find a Monte Carlo representation of these probabilities, then this is basically the solution of the PDE. Okay, the update step is incorporating the observations then at time t, and this is just Bayes rule written over here. Right? So that gives a recursive relation going from some time to time t minus 1 to time t, and I'm just going to talk about discrete time cases here. And so as a formal solution, this is the solution. I'm just showing it as a in graphical language here, but we'll skip this. There are two important Monte Carlo methods that are used in practice, and they have their pros and cons, which I will talk about, which are both. One is called ensemble Kalman filter, which is based on some Monte Carlo representation of Kalman filter, which is exact in the linear case, and so even the ensemble Kalman filter is only exact in the linear case, but is approximation in a nonlinear case. And the other one is a particle filter, which does not have any restriction in terms of linearity of the dynamics of the system at all. Okay, so the Monte Carlo approximation essentially represents both of these steps, the prediction and update, by using a Monte Carlo sample out of these probability distributions. So maybe I will talk about the last part first. The prediction step is essentially just the forecast model, as I was explaining in the slide before. So to go from time t minus 1 to time t for each of the Monte Carlo sample, each particle in the Monte Carlo sample, it's simply solution to the model that we have, deterministic or stochastic. The difference between the two methods essentially comes at the step of updating or using the observations to make a Bayes update. And this in the particle filter is done by updating weights. So particle filter uses a weighted sample or importance sampling representation of the distribution. And in this case, the weights are updated in order to take into account the observations. So this is some sense writing out, you could think of it as writing out a Bayes rule, Bayes theorem for a Monte Carlo representation. The ensemble Kalman filter does not actually do anything along these lines, but rather it uses the Kalman update, which as I said, is exact for linear systems, and just apply Kalman update to each of the ensemble members, to each member of the sample. And in a way, it's an unweighted sample, so the weights are just 1 over n. Okay. Actually, sorry, I just realized that I forgot to take this away details on the next slide. I don't have a next slide with details. Anyway, so now these two filters suffer from their own difficulties. Particle filters can deal with nonlinear systems, but they suffer from curse of dimensionality. So in high dimensional systems, they lead to a problem that is the curse of dimensionality shows up as the weights going to 0 for a large number of particles, and you need to introduce resampling methods. And ensemble Kalman filter, since it's based on Kalman filter, assumes or requires some kind of Gaussian assumption, or rather, the other way to put it is, as an algorithm it works, but if the distributions that are encountered are highly non-Gaussian, then the ensemble Kalman filter does not work well. And where does the dynamical system or chaotic aspects come in? So that's one slide here, which is that just shown here is a simple Lorentz system, and this is what is called a butterfly attractor, the Lorentz attractor. And in a way, that the meaning of the attractor essentially is that almost every trajectory looks alike. That is, the statistic of almost all trajectories will be the same, and or ergodicity is valid on the attractor. But then the trajectories will actually diverge away from each other exponentially fast, which is what is shown on the right. So these two might sound contradictory, but they're not. But the first one is about statistics, the other one is about the time series itself. And so that's a positive, that's a property of systems with positive Lyapunov exponent. And the key point for deterministic dynamical systems is that the attractor, for example, the one that we see here, is not absolutely continuous. So there are examples where the attractor is absolutely continuous, but in most cases in practice, it is not. And unfortunately, all the resampling methods that I know of work with absolutely continuous distributions, and hence, when you apply resampling to possibly in Monte Carlo methods to problems like this, where the underlying distribution is actually not absolutely continuous, it leads to error that essentially cannot be controlled well. So this is effectively the reason why none of the known numerical filters, the ensemble-Kalman filter, because it has some assumption about Gaussianity, linearity, and a particle filter, which needs resampling, which does not work well for distributions of this type. And so both of these or any of these other methods do not work well, or do not work in quotes right now. As I said, it's not quite a theorem yet, in the sense that, yeah, I would like to prove that it cannot approximate the exact filter, even in a large sample size limit. But okay, anyway, so given all this, at least a desirable property is stability, in the sense that difference in the initial conditions of the filter should not have large effects on the filter itself. So, by the way, stability of the filter, I don't mean stability. These systems are not, well, they have a stability of some kind, but anyway. Okay, so that's the next part, and that's where first of the machine learning methods will come in, which is trying to assess the stability numerically. So before going to numerical methods, just a definition. Maybe just look at the pictures, and thanks to Pinnock for this picture. You take a flower and a starfish as an initial condition of the distribution for the filter, and eventually as time progresses, we want the filtering distribution to be same or similar or very close to each other in time as time t goes to infinity. And so this is the asymptotic notion of stability, that you start with any distributions mu1, mu2, the distance between those distributions, the filtering distribution at time n, as time n goes to infinity, should go to 0. And in this case, I haven't said what distance to use, and that's what I will come to next. So for this part, all this complicated notation of conditional distribution and so on is replaced by simply pi n, making explicit the dependence on the initial condition, because that will be the main focus. Okay, so given this, how do we assess, how do we test the stability of these filters? And in order to do this, we basically use what is called a sync-on divergence. And I guess here are some definitions. Basically, what we want is some distance that we can compute numerically between distributions which are obtained as Monte Carlo samples on high dimensional systems. The high dimensional part actually is something we haven't quite applied it to very, very high dimensional systems yet, but that is still work in progress. And that is the key point. And here are basically some definitions of finally, eventually, what will be used in the computational, in actually numerically computing this. So we will be computing what is called a sync-on divergence. And the sync-on divergence between the two distributions mu and nu is defined as some kind of symmetrized version of this distance, which is related to which incorporates both W2 and the KL, the Kuhl-Black KL divergence. Sorry, and I mean, right now it's just a definition. The point is the algorithm to develop, sorry, the algorithm to compute this sync-on divergence was recently, I don't know how recent, I think about 6 or 8 years ago, 10 years ago, developed as the motivation was mainly coming from machine learning approaches where you're looking at problem of images and you want to have distributions over these images and want to find the distance between them. But anyway, that's aside. And this is the algorithm that came from this machine learning community. That is what we have used in order to compute this synchron divergence. So it's a divergence. So I guess there is a problem, which is that it does not satisfy triangle inequality, but that does not quite okay. Anyway, it's not something that's crucial for us to assess numerically in assessing the stability. So okay, and it has a property that as there is a tunable parameter epsilon, and as that parameter goes to 0, it approaches the distance. So, but then we can. This is computed at finite epsilon. Okay. So what the result that I will be showing will be on a couple of models. As I said, the Lawrence model, which I showed earlier, and there was another model, Lawrence 96. And this is a model that can be scaled to any dimension. It can be stated in Lawrence 63 is a 3-dimensional system, but Lawrence 96 is basically an n-dimensional system, and we chose n equal to 10 or 40 as illustration, and much higher dimensional systems are something that we will look at later. Okay, and the process is simple. We choose multiple different initial conditions for the filtering distribution and try to assess the distance, or in particular, sorry, the synchron divergence between these filters at later times, and figure out whether they are stable or not. And we do it for the ensemble Kalman filter and a particle filter both. So these are the results for the particle filter. And so the particle filter seems to be extremely stable in the sense that the distance, the initial condition is forgotten extremely quickly in this case. So currently what we are doing is trying to understand what the rate of decay is. It seems to be exponential, and we are trying to understand what this rate is and how to relate it to the dynamics of the system. But what is basically plotted here is the distance, or in particular the synchron divergence, as a function of time, assimilation step n, and you can see that the distance has actually dropped to not quite 0 because yeah, so of course numerically the distance between finite Monte Carlo samples of the two distributions does not really go to 0, and this can be well understood. So you can numerically take samples of larger and larger size and look at the effects of how small the distance can get, and theoretically you know the distance to be 0. So, okay, but the particle filter implementation does seem to be stable, which is good, and even for a deterministic dynamical system. But by the way, just to point out what I said earlier, there are no theoretical results stating that as n goes to infinity, the particle filter the sample size going to infinity limit will actually lead to the correct filter. That does not exist for deterministic dynamics. So we purely have to rely on the numerics in this case. Okay, similar things for ensemble Kalman filter, except that it does not stabilize. The distance does not decay as a function of time as quickly as it does for the particle filter. And this is something that is not completely well understood. I don't know why this is such a stark difference between the two. And oh, sorry, I didn't put this plot here, but we also looked at, so these two are two different numerical implementations of the same exact filter that we want to approximate. So natural question would be to understand the distance between the ensemble Kalman filter and a particle filter. And that also decays, but does not go to as small a value as this. So in a sense, both the filters are stable by themselves, and hence as time t goes to infinity, but with exponential decay, the t goes to infinity is not really infinity, it's some small number of steps. Then both of them give distributions which are stable amongst themselves. So EnKF is stable, particle filter is stable by itself, but they don't come close to each other. So they remain distinct. And so then natural question is which one should be used? And this is something we are still investigating as to how to assess. Even if there are multiple stable filters, then which one is a better one? Okay, so that's, I guess yeah. Another maybe 10-15 minutes. Yeah, okay, fine. So maybe I'll skip this figure for now. This is just an illustration, but anyway. And let me come to another application of machine learning methods. In this particular case, actually using neural networks for solving Fokker-Planck equation. So why Fokker-Planck in the first place? Never appeared up to now in this talk. But remember the predict update cycle of the filter. So you going from time t-1 to time t by a forecast step or a prediction step and then a update. And when the model is actually derived from, let's say, stochastic differential equation of the form written over here, then this prediction step going from time t-1 to time t is basically a solution to a Fokker-Planck equation. The Fokker-Planck equation for this stochastic differential equation is written over here, where the operator L is simply defined in this case. And so basically, if you take this as if you take the distribution, the filter at time t-1 as the initial condition to Fokker-Planck, and then solve it up to time t, then an update. Of course, so I guess towards the end I will say about how try to combine both the steps together. But for now, let's just think of the prediction step. So the natural question is, can we solve a Fokker-Planck equation? Of course, if you want to try to solve it in very high dimensional spaces, in high dimensional problem, this will be a difficulty. And that's where the neural net methods come in. As we heard in the previous talk by Professor Mishra, these kind of networks can be extremely efficient in trying to solve these kind of equations, but not exactly these kinds. So there are a couple of problems I'll mention in the modification that we need to do in order to be able to solve this. And in particular, the idea is we want to solve this equation in some sense by two steps. I'll come to why the two steps are necessary. Is first find the stable or the asymptotic solution to this Fokker-Planck equation, and then use the asymptotic solution in order to find a backward solution to the Fokker-Planck in some sense. So the details will come clear now. And there are two broad categories of the problems that Pinak has worked on, my student Pinak Mandal. And those are basically where the drift itself is a gradient flow or it's not a gradient flow. And these are some of the examples for which the numerical results will be shown later. So again, Lorentz model or a gradient flow which has an attractor, which is just a simple unit circle. Okay, and in the first case, the gradient flow, the steady state of the Fokker-Planck equation can be written down explicitly, whereas in the case of non-gradient flow, no analytical solution is available, and physics informed neural nets is what we used in order to get this. Okay, so I'm not discussing any of the details of the physics informed neural net itself. It's probably not the most efficient one available or something. It's just something that the point was not necessarily to make this the most optimal way to solve this PD yet, eventually, but anyway. And as an illustration, this is the gradient flow case. And of course, in this case, the actual solution can be computed or written down explicitly, as I said earlier. So this is the actual solution, the true solution, that is the steady state. And this is what is obtained by using the physics informed neural net. And they are actually quite close. And as you can see from this picture, or you can assess it better. And in the case of the non-gradient flow, there isn't any steady state available explicitly, but we can at least try to simulate the original stochastic differential equation and try to get a approximation of this. And what is shown on the right is by using the simulations of the stochastic differential equation, and what's shown on the left are the physics informed neural nets. And so they do seem to come close. You can see that there are possibly some differences, and we have to understand better what those differences are and why they come about, and so on. But so this is just the first step in trying to solve the time-dependent Fokker-Planck equation to find the steady state first. And but before I go to why we want a steady state, just recall the connection between a PDE of the form given over here and a stochastic differential equation written over here through the Feynman-Kac formula, which is written here. Yeah? So this is used for calculating the time-dependent solution of the Fokker-Planck equation. And there are two difficulties in trying to apply this directly to the problem at hand. And one of them is that the drift term, the mu in the equation, needs to be globally Lifshitz, which is not the case, for example, for Lorentz system. And so we have to overcome that I will not discuss in detail here. Essentially, the idea is to use the fact that there is an attractor, and if you essentially focus your attention on the attracting region and outside it let mu go to 0, then that will be a global Lifshitz approximation, and then we have to so there's a we have proved a theorem which is that those two approximations can be are close to each other. So anyway, so that's one. And the other one is the lower boundedness, which in this case is the divergence of mu. And that's one of the problems in the equation that's written over here. Right? So if we apply it to the original problem by itself, this cannot be overcome. And the way to overcome this is, instead of trying to solve it for P, you solve it for a slightly different function h, where h is simply written over here, right, in this form. And this is what Pinnock came up with. And then it turns out that basically h satisfies the equation like this. And as I said, this is something that looks like this like the PD associated to a SDE, where this is the drift term now. And knowing the form, remember the form that I wrote down for P infinity, using that you can show that this actually now is nice, and it can in fact be bound. There is the lower boundedness property, and yeah, anyway, so that's a trick in a way in order to use the Feynman-Kac formula, but get over these problems of lower boundedness of the Q and the global Lifshitzness of the drift term. So using both of these, then we could implement the time-dependent solution of the Fokker-Planck equation. And in this case, these are some of the results shown here. This is the simulation of the Fokker-Planck using Monte Carlo simulation of the stochastic differential equation, whereas the left-hand side is using this neural net plus. So the P infinity or the steady state is computed first, and then the Feynman-Kac representation is used in order to compute the time-dependent solution. And they are close to each other. And again, we still have to fully understand how it works well, and what could be the pitfalls. And so in this case, even in the type 1, the category 1, which is the gradient flow, the exact solution to the Fokker-Planck is not known, or time-dependent exact solution. And hence both of these are basically numerical results, and we have to just assess the differences between them numerically. And similarly for the Lorentz system, but I'll not discuss this much. So just to conclude quickly, the main challenges in data assimilation problem, which is basically mathematically purely a nonlinear filtering theory problem, are the fact that the systems that we want to consider eventually are high dimensional systems that leads to curse of dimensionality, for example, for the particle filter. And these are complex and chaotic systems. That means the distributions involved are not Gaussian, and the non-Gaussianity, for example, affects the Kalman filter based methods or other methods which are in some sense more suitable for linear systems but used for nonlinear systems. And because of this, the common filters like the ensemble Kalman filter, particle filter do not approximate this problem very well. And what I focused on in this talk were two specific questions. One is, how do you numerically assess filter stability? And in particular, what we used was the synchron divergence and illustrate that these filters are numerically stable, but the relation between stability and accuracy of the filter, or how well does the filter do, is still something that we are investigating. And the other one was to use physics-informed neural networks to solve at least one step of this filtering problem, which is to solve the Fokker-Planck equation. And that is something that we are still continuing to work on, which is one, of course, is to actually apply to high dimensional problems. But nominally, this thing should scale linearly in dimensions. And so let's see how well does it actually do these physics-informed neural networks for high dimension solutions of high dimensional Fokker-Planck equation. And the next step is to incorporate these solutions into the filtering, or rather in some way combine the predict and update step into one in order to find basically the time map from time t-1 to time t, but for the distribution themselves by using physics-informed neural networks or by using neural network methods in general. And some of these codes actually to implement this are available in PNUC's Git repository. So if you want to take a look at that, please, I'll be happy to discuss more about this with you. So with that, I think I will stop. Thank you.